Okay, now let's move on to the outer boundary conditions. What color did I use for this, by the way? Oh, yeah, use blue. So I'll continue. I'll use orange this time. Yeah, that should be nice. So now we move on to the outer boundary conditions. Okay, now we need to recall that we actually have 3 possible outer boundary conditions, and I'm going to list them down over here. The first is assuming that we have an infinite acting reservoir. So this means that the pressure transient has not yet reached the boundary. Okay, so for the infinite acting reservoir, typically our, and I'll just use orange for this one. We write the condition as P when radius goes to infinity at any time is simply equal to P sub I, because we assume that the pressure at any location before the boundary is equal to P sub I, and we assume that the reservoir is infinitely large because the pressure transient has not yet felt the boundary, so we can just write it in this way. So the question is, how can we rewrite this in dimensionless terms? That's actually fairly simple. We can just rewrite it as follows. Okay, so now the question is, where does this come from, where does this come from, and where did this come from? So using the logic from the previous part, if r goes to infinity, then so does r sub d. Because, let me scroll down a little bit. Because r is equal to r sub d is equal to r. Alright, and how about this? Well, t sub d scales linearly with time, so this is valid. And how does this equal to 0? P sub d when p is equal to pi is 0. Okay, so that's it. It's pretty simple. Next condition. The next condition, we assume that there is a no flow boundary. So we assume that the pressure transient has already reached the boundary, and we assume that there's a no flow boundary. So when there's a no flow boundary, we can use Darcy's law to say that the flow is equal to 0. Q is equal to 0 at the boundary. Now recall that Q is equal to K over mu dou P over dou R times the area. And also recall that K, mu, and area, and also the flow rate, these are all constants, and they are all positive. They are all defined to be larger than 1. Therefore, the only term that can be 0 is dou P over dou R is equal to 0. Okay. Now, I've already showed how we can convert this to a dimensionless form in the previous part. So without doing too much of the legwork, I want you to convince yourself that this can actually be rewritten as negative 1 over r sub w multiplied by 141.2 qb mu over kh over that, yep, multiplied by dou p sub d over dou r sub d, that is equal to 0. Okay, now if you're wondering where that came from, I'll just quickly write that down over here. So remember, r is equal to r sub d, r sub w, and p is equal to p sub I minus 141.2 qb mu over kh times p sub d. So if you break this apart, you'll get the expression above. And using a similar logic, given that r sub w, k, h, q, b, and mu are all constants, and they're all positive, we have that dou p sub d over dou r sub d is equal to 0. Finally, we know that this is at the outer boundary. This is happening at the outer boundary where we have no flow. So this is happening at dou pd over dou r sub d at the boundary. So at the boundary. So the boundary is defined as RE. So R sub E. This is the extent of the reservoir. We can also define R sub E D is equal to R sub E over RW. And finally, we can rewrite the condition as dou PD over dou RD at R over E, RE sub D is equal to 0. Okay, so what color did I use to the previous one? I used white, yeah, so I'll use white here as well. So this is the outer boundary condition when we have a no flow boundary. Last but not least, we will look at the outer boundary condition for a constant pressure boundary. Constant pressure boundary. Okay, so if we have a constant pressure boundary, well, typically we write that as P when R is equal to R sub E and T is equal to 0. This is equal to P sub I, the initial pressure. So if we just use the logic from the previous two derivations, we can just rewrite this as follows.